Good evening. Welcome to another fun-filled Wednesday evening. Tonight, I'd like to get us back to OIDD 611, and we're going to move on to sort of the second half of what you've discussed in lecture so far, and that's the introduction of variability. And really there are two key parts of this. One where we have infinite patience. In other words, people coming in to your service, whatever, or products coming in are willing to wait in order to be serviced. And so they'll sit there and wait as long as it takes your service to get to them. But the time or the rate at which they arrive is variable. So we don't know, we can't look at it and determine exactly when things are going to happen, when things are going to work out, as we did in the earlier sessions a couple of weeks ago, 4 weeks ago. The other possibility, the other extreme, is where someone coming into your service is not willing to wait at all, unable to wait. And I think a typical example of that was the emergency room trauma center. If your trauma center is all blocked up and you can't accommodate another patient, the ambulance can't come in, they have to be diverted to some other place. So there's kind of two extremes. And of course, the real world is somewhere in the middle. It's a little bit more complicated when you look at both of those. But tonight we'll examine some problems that cover both of these two extremes. And we'll look at a few variations, like what's the impact on cost, and what kind of staffing should we have in order to optimize service, that sort of thing. So the plan tonight is to work through some chapter problems from the textbook. These numbers are from the 3rd edition. And so if you have a different edition, you'll have to translate them. We may not have time to go through all of these. That's okay, but we'll try to hit the main ones: 8.2, 8.5, 8.6, 9.1, 9.4, 9.6, and if we have time, a fairly complex one, 10.2. Any questions before we get into it? Okay, well, let's go ahead and dive into the first one. There's a lot of text here. Wow. Question 8.2, mylaw.com. It's not that hard a problem, but it's a long problem statement. It's a recent startup trying to cater to customers in search of legal services. So lawyer in a website. They will allow for extensive interaction between lawyers and customers via telephone and internet. Processes used in the upfront part, largely consisting of answering some basic customer questions prior to entering a formal relationship. A lot of detail here you don't need. Customers are encouraged to send emails to mylawyer@mylaw.com. From there, the emails are distributed to a lawyer who is currently on call. Given the broad skills, any lawyer can respond to each incoming request. Now we get to some of the nitty-gritty here. Emails arrive from 8 a.m. to 6 p.m. at a rate of 10 emails per hour, with a coefficient of variation for the arrivals of 1. So this is like a Poisson distribution, or a kind of your normal arrival rate. Notice that it's 10 hours. We have 10 emails per hour, so we have an average of 100 emails a day. At each moment in time, there's exactly one lawyer on call, so we have one resource to handle these requests, the demand. It takes a lawyer, on average, 5 minutes to write the response, and the standard deviation of this is 4 minutes. And so we've got some questions. What's the average time a customer has to wait? This includes the time that the email sits in the inbox and the time that it takes the lawyer to write the email. How many emails will a lawyer have received at the end of a 10-hour day? When not responding to emails, the lawyer on call is encouraged to actively pursue cases that potentially could lead to large settlements. How much time on a 10-hour day can one of these lawyers dedicate to this activity? It's a side task that they can do when they have idle time. To increase the responsiveness of the firm, the board of mylaw.com proposes a new operating policy. Under the new policy, the response would be highly standardized. So they're going to go using a script. And that doesn't reduce the average time to write the email, but it does change the standard deviation. It reduces the variability. And then 2 more questions based on that. How would the amount of time a lawyer can dedicate to the search for large settlement cases change with this new operating policy? How much idle time will we have as a result of this? And how would the average time a customer has to wait for the response change? So, a lot of stuff there. Very simple picture though. We've got one lawyer in a box. We have emails coming in. Essentially, there is a buffer here, the email inbox, and so these emails are going to sit in a queue here until the lawyer can get to it. On the arrival side, we've got 8 a.m., 6 p.m., 10 hours, and we have 10 emails per hour coming in on average. And they come in variable times. We know that the coefficient of variation is 1. That is, it's a Poisson distribution of arrivals. And then we can figure out, of course, that the arrival time, the inter-arrival time, which we normally use variable A for. And here's where we're going to have to do a little bit of arithmetic because we want to make sure all of the units are consistent. And so I'm going to work in minutes here because we've got hours, we've got days, we've got minutes for response times, that sort of thing. So I'm going to put it all into minutes. So we have inter-arrival time of 1 in 1 hour, we have 10 emails. And to convert that to minutes, we have 60 minutes per hour. And so that makes our inter-arrival time 6 minutes on average. That's it for the arrival side. How about the activity or the process? We know that on average, it takes 5 minutes to write a response. So that's our processing time. That's on average. And that the standard deviation of this time is 4 minutes. And of course, we can extract from that information that we have a process time P of 5 minutes. And our standard deviation, of course, of 4. With that, we can calculate the coefficient of variation for processing as the standard deviation divided by the average processing time. That works out to be 4/5 or 0.8. And you'll notice that the coefficient of variation is essentially a scaled standard deviation. We put it in the same scale as the average. Next thing we want to do, I'm sure we're going to need some utilization numbers, And so I'm going to go ahead and calculate that. What's the utilization of this process? This lawyer, how are we utilizing the lawyer? And again, we use U for that variable. And utilization is the flow rate divided by the capacity. And this is not implied utilization, this is utilization. If we're looking at implied utilization, we're looking at the demand rate instead of flow rate. And that's going to be, what's the flow rate of requests coming in? It's 1 over the inter-arrival time, A. What's the capacity? It's the rate at which the lawyer can process these things, and of course that's 1 over the process time. And that looks a little bit nicer when we do it P over A, and that's going to be 5 over 6, inter-arrival time of 6 and processing time of 5, and so our utilization is going to be 0.83. I'm sure we're going to need that number somewhere along the way. Okay, so that's what the activity looks like. And again, this is a case where the emails are coming into the queue and they will sit there forever, as you know from your own email inbox. They'll sit there forever until somebody answers them. So the lawyer will pick them out in order, write up his response, takes about 5 minutes on average, send them back, and he moves on to the next one if there's one there. And of course, since his utilization is less than 1, it means that we're not going to have an explosion of emails in the queue. Okay, so what's the average wait time? And we normally call this, as I've labeled it up there, the time in the queue. See what the question said. What's the average time a customer has to wait for the response to his or her email, ignoring any transmission times? Notice, this includes the time it takes the lawyer to start writing the email and the actual writing time. So the wait time is going to be a combination of the time in the queue or the inbox plus the processing time. So you just have to read the language carefully. Sometimes they'll be asking how long does a customer have to wait before they get entered into the process. In this case, how much time do they have to wait between when they sent the email and when they get the response back? So there's the 2 parts of that, the queue time plus the processing time. Let's first look at the time in the queue. How do you spell queue? Too many U's and E's. That's TQ. And for a case of a single resource here, it's a simplified formula. So it's processing time times a factor related to the utilization, and then a factor related to the variation or variability in the arrival times and the processing time. So the coefficient of variation for the arrival squared plus the coefficient of variation for the processing squared, all divided by 2. So you recognize this is the mean of the sum of squares of the variations. It might kind of bring up some nightmares from statistics. But anyway, we can go ahead and plug some numbers in there. 5 for the processing time, 0.83, good thing we calculated that, and then 1 minus 0.83. And then we can also throw in our numbers here for the coefficients of variation, 1 squared, and then 0.8 squared, all divided by 2. And if you plug that into the calculator, you get 5 times 5 times 0.82, which works out to 20.5 minutes. And this is the email sits in the inbox on average. So what's the total flow time? That's going to be the queue time on average plus the processing time, P. And we now know both of those numbers. So 20.5 plus 5 equals 25.5 minutes average time to get a response. Nothing hard about that. Just remember that you have, by reading the question carefully, it is the combination of the queue time plus the processing time end to end. That's the total flow time in this. The queue time is given by this formula. Don't need to know how the formula is derived as long as you've got it on your cheat sheet. So there's a question. Belisa says, why are you not considering the square root of 2 times m plus 1 minus 1 in the TQ? It's a very good question. And to answer that question, notice what she's referring to is this term. And this term is the simplified form for a single resource. And since in the formula for multiple resources, a pooling of resources, the 2 times m plus 1, if minus 1, if you put in 1 for m, it's 2 times 2 square root 2 minus 1, and it comes out to 1. So essentially, it reduces to this form. And we'll have another problem a little bit later this evening where we've got more than one resource where m is greater than 1, and we'll be using the full formula for that. What I would normally do on a cheat sheet is I would put the complete formula in on the cheat sheet and then realize or remember that if m is 1, it kind of reduces to a more simple form, but I don't have to keep both versions available. Make sense? So the next question, B, is how many emails would the lawyer have received at the end of a 10-hour day? How many emails? And this is really straightforward. As long as we have the utilization less than 1, then it's fairly straightforward. We have 10 hours in the day, and we're getting on average 10 emails per hour. And that works to 100 emails per day that the lawyer sees. Yes, it is that simple. Sometimes the questions are not designed to trip you up. But if the utilization were greater than 1, then you have a problem, because you'd end up with a queue that was just building and building up over the day, and the lawyer would not be able to handle all of them. He'd be basically backed up, and at the end of the 10-hour day, he would not have handled or would not have received or seen all of the emails that came in. So he'd be seeing something less than the total number of emails that were coming in. How about the next one? The next question is C. When not responding to emails, the lawyer on call is encouraged to actively pursue other cases so they could do other work, background work. How much time on a 10-hour day can the lawyer dedicate to this activity, assuming that he can instantly switch back and forth? So what we're looking at here for part C is background work. And so since his utilization is not 100%, he's got some idle time. And that idle time we can calculate an average for. How much idle time does he have? We can work with averages here. And realize that his processing is going to be 5 minutes. The inter-arrival time is 6 minutes. So on average, once every 6 minutes, an email comes in. So on the average, for every 6 minutes, or 1/10 of an hour, he or she is going to have 6 minus 5, 1 minute of idle time. So you can see if you, for a moment, ignore the variability, if an email comes in every 6 minutes and he takes 5 minutes to process it, when he's done, he's got an extra minute of time to twiddle his thumbs or work on background work. And then again, we're going to have to just convert units or look at overall time. So for every hour, he's got 10 times 1 minute of idle time. And for 10 hours, just multiply that by 10. And so total, we have 100 minutes of idle time for background work. And of course, if you can't switch back and forth without some overhead, then you wouldn't be able to make use of all those 100 minutes. That's a straightforward one, is very easy answer, but if we want to look at it a little bit more rigorously or formulaically, his active time, that is the amount of time that he's going to actually be working on processing emails, total time times the utilization, and that's going to be 10 hours times 60 minutes per hour. So that's the time part. And the utilization, as we saw before, was what, 0.083, which is 1 minus 0.083, which is 5/6. And that works out to be 500 minutes active processing. So the idle time is going to be T times 1 minus the utilization. And that will be 10 hours times 60 minutes per hour times 1 minus 5/6, and that equals 100 minutes. So in a 600-minute working day, he's got 500 minutes of actually responding to emails on 100 minutes of idle time that he can use for background work. Okay, no questions so far. What's the next problem we have to answer? Okay, so we're going to now use standardized scripts. And the idea behind using a standardized script, in other words, he's got a selection of common responses, and he's just going to pick the appropriate one, do a little cut and paste and rewording, that sort of thing, in order to respond to the incoming email. And he can take advantage of this because, you know, the vast majority of questions coming in are fairly standard. They're fairly consistent. And so he can pick from a number of responses. It's very typical in a call center kind of operation. But by doing that, the idea is that if you reduce the variation in the time that it takes to process that email, what impact will that have? Hopefully it'll have some improvement. And so two questions. With this new policy, with the amount of time the lawyer can dedicate for background work change, and with the amount of time the customer has to wait for the response change on average. Let's take a look. So now use standardized scripts. And the important thing is you're now reducing standard deviation to half a minute. But recall that the processing time P is still 5 minutes. How will this affect idle time? Or, yeah. So again, remember, we're less than 100% utilized. That means that the process is demand limited. So we do have the idle time. And that means that 1 over A is less than 1 over P. The incoming flow rate is less than the capacity, and therefore accumulated idle time. It's still going to be a function of averages. And by the equations or formulas we've used, we're going to see that the idle time total, average, is not changed. Because we got a Q in front and because we have utilization less than 1, the lawyer can pick up a new email as soon as he's ready to process it. He'll process it in on average 5 minutes. A little less variability than it was before, and so that's going to affect how much variation he has in the idle time in between emails that he processes. But on average, overall, during the day, the amount of idle time is still going to be the same, and the processing time is going to also be the same. Next, we're asked what's the average wait time for the customers. And of course, this is a combination of the queuing time plus the processing time. The average processing time is unchanged, but the queuing time does depend on variability of the processing. So we're going to plug that in to our TQ formula. And for a single resource, remember, utilization divided by 1 minus utilization times CVA squared plus CV for the processing squared, the average of those two. And you can see that this is dependent upon, come on, here we go. A change now in the processing times variation. It's going to be 0.5 divided by the processing time 5. Now it's 0.1. And so our queue time will be 5 times 5/6 over 1 minus 5/6. And the variation factor will be 1 plus 0.1 squared over 2. And you can see that's a smaller factor. So the answer from the calculator is 12.83. And so the total wait time for the customer is going to be that plus the processing time on average, and that's going to be 17.63. Sorry, 12.63 plus 5 is 17.63 minutes. So this is now shorter, and you can compare it to the original time, which was 25.5 minutes when the processing time had higher variation. So you can see that although we're dealing with averages, we have variation in both the arrival time and the processing time, and that variation in either one of those will impact the amount of time that the customer or the demand or the incoming email spends in a queue waiting to be serviced. Any final questions on that one? That's pretty easy, right? Not a lot confusion there. Okay, no questions. Let's move on to the next one. This is 8.5 in edition, third edition. I don't know what edition is the textbook up to now. Is it fourth or is it still at third? I'm not sure. Anyway, Atlantic Video is a small video rental store. They're open 24 hours a day. Customers arrive around the clock. 30 customers arrive every hour around the clock. They have a standard deviation of inter-arrival times of 2 minutes. So this is the sigma of A. There's one checkout employee. Again, we have one resource who needs on average 1.7 minutes to check out a customer. Standard deviation of checkout time is 3 minutes. So this looks a lot like the previous example. We've got essentially one resource sitting there doing some processing. Takes 1.7 minutes to process. It's variable that time, standard deviation of 3 minutes. We've got people queuing up, standing in the checkout line, and so we have basically the same kind of operation. So the key points here were we're running 24/7, 30 customers per hour with a standard deviation of 2 minutes on the inter-arrival time. Now, of course, we got units changes there. We have one resource available to do the processing. The processing time takes 1.7 minutes on average, and a standard deviation for that processing time of 3 minutes. So you can see there's a pretty wide variation there. Let's calculate some useful information. I know we're going to need it. So what's the inter-arrival time in minutes? We have customers per hour arrival rate of 30 customers per hour. We'll take 1 over that to find the minutes per customer. But we have to convert by multiplying that by 60 minutes in an hour. And that comes out to 2 minutes per customer. That's the inter-arrival time. Our utilization, remember the utilization, it's the ratio of processing time to inter-arrival time times the number of resources, A times M. But here M is 1, so this is going to be 1.7 processing time divided by the 2 minutes per customer inter-arrival time. That's going to be a utilization of 85%. And we know we're going to need the coefficient of variation for each of these. So CV of A, no surprise there. 2 divided by 2, that's 1. And of course, that's standard deviation divided by average. So that's what you would expect for a normal Poisson arrival rate. And our coefficient of variability for the processing is expected to be different, of course. A lot of variation there for a small average time. That works out to be 1.765. Okay, so those are the key parameters we're going to need. We've got A, we've got P, we've got our coefficient of variation for each of those, and we have our utilization, which we do know is under 1, so we are able to handle that queue as long as people are willing to wait. Assuming that every customer rents at least one video, so every customer coming in at a rate of 30 customers per hour will eventually pick something and will be waiting in the queue to be checked out. What's the average time a customer has to wait in line, not including the actual checkout time? It was a little different question than the previous one. The previous one, how much time did the customer have to wait for a response to his email? That meant he had to include the queue time plus the processing time. This question, the way it's written, says what's the time the customer waits in line, not including the actual checkout time. So just the TQ part. And of course, here's where we have, I'm gonna put in Belisa's full formula. Processing time divided by the number of resources. And here's the big impact on utilization. U times this funny term, the square root of 2 times the number of resources plus 1. All of that minus 1. So U to that messy thing. And then 1 minus the utilization in the denominator. And then we'll have the same variation term, coefficient of variation for the inter-arrival time, plus the coefficient of variation for the processing times, all those squared divided by 2. Okay, so this formula looks very similar. The difference here, there are 2 places, and this is where the number of resources comes in. There's a 1 over M factor, 1 over number of resources, because the more resources, the each resource reduces the queue time. And then this utilization factor is adjusted by those number of resources as well. Instead of having just the utilization rate on the top in the numerator divided by 1 minus the utilization rate, we adjust that numerator part. Now, again, it's going to be m is 1. So this is going to revert to that simplified formula. But like I said earlier, I would just put this one on the cheat sheet, and then anytime I needed a single resource calculation, I can go ahead and do this. So 1.7 divided by 1, and that whole mess is 0.85, which is just the utilization that we calculated earlier, and then 1 minus that utilization of 85%. And then we have a Poisson inter-arrival time, so that's coefficient of variability is 1, and then a higher coefficient of variability for the processing time. We'll average those two squared, and it works out to be the time that the customer is waiting in line at the cash register, checkout stand, I guess, is 19.82 minutes. I'll tell you, I wouldn't be willing to wait in line for nearly 20 minutes to check out a video. I guess that's why streaming services are so successful. Anybody actually remember video rental stores? I do. They made their money on late charges. Hated that. Okay. Yeah, Blockbuster, they charged almost nothing for the video, but they charged you an arm and a leg if it was late by 1 minute. And they had this what is it, $1 to rent for 1 day, but the 1 day didn't include 24 hours. It was dependent upon what time you rented it. So a lot of people got tricked into actually paying the $6 late fee for the $1 video rental that they returned the next morning. I hated that. Anyway, so now there's Netflix. If there are no customers requiring checkout, the employee is sorting returned videos, of which there are plenty. He's always got as many as he needs to sort. How many videos can the employee sort over an 8-hour shift if it takes exactly 1.5 minutes each? Again, this is a background task, just like in the previous question. And we already learned that it really is only based on averages. And if we're looking for idle time, in order to do background work, we recognize now that that's going to be based on averages, even though we have variability in the time that customers arrive and the variability in the time that it takes to actually process them, check them out. So the idle time, I'll call it I, is going to equal the cycle time times the number of resources available minus the activity time. So this is the formula you would use if you had one or more resources to do this. So the cycle time times the number of resources you have to do that processing minus the activity time. In other words, it's AM minus P. And in this case, we have 2 minutes of inter-arrival time times one resource, one checker, minus 1.7 activity time, and that says we have 0.3 minutes per customer. And that's an important distinction because now we have to figure out the total based on the number of customers that we have. And that's going to be 0.3 minutes per customer times the 30 customers per hour that we have coming in times the 8 hours per shift equals 72 minutes per shift for the employee. And since videos take a minute and a half to sort, we take the 72 minutes available in a shift divided by 1.5 minutes per video, and that equals a grand total of 48 videos sorted per shift, per 8-hour shift. That's our answer here. We can also, like we did before, we can use the utilization numbers. And the total idle time. One minus utilization, that's the part that's not being utilized, times the total time. And since I already calculated that, the utilization is 1 minus 0.85 or 0.15 times 8 hours times 60 minutes. We're going to be doing it in minutes. Equals 72 minutes per shift. And number of videos sorted is again 72 minutes divided by 1.5 minutes per video. That's going to be 48 videos sorted per shift. Same answer, no surprise, right? And you realize by using the utilization number, utilization also has a factor of 1 over m in it. So both of these methods, both of these formulas take into account the number of resources you have. In this case, again, I generalized it to formulas for more than one resource, but we only have one in this particular example, so m is 1. Hopefully, Belisa, that kind of demonstrates the difference. Okay, what's the average number of customers at the checkout desk, either waiting or being served? Now, this is similar to the previous problem where we had to look at the queue time plus the processing time. And it's the number of customers. So we're not looking at the time, but the number of customers. So how do we figure that out? Well, let's go back to Little's Law. If we need the inventory, that is the number of customers in both the queue part and the processing part, we're going to have to take time and multiply by flow rate. Well, the time, of course, is the queue time plus the processing time on average, and Little's Law deals with averages. And the flow rate, again, we're going to have to deal with a units conversion. 30 customers per hour times 1 hour per 60 minutes. And that works out to 19.82 plus 1.7 times 1/2. So the inventory in the queue and the process is going to be 10 1.76 customers checking out. Now you can see why there's almost 20 minutes in the queue, because they've got a line in front of the cash register of 11 people on average. They need some more people there. Okay, now we're going to get a little bit more complicated. What if 10% don't rent a video and do not go through checkout? So we've got customers arriving, 30 customers per hour, but only 90% of them actually go and rent a video and are standing in the line waiting. What's the average time a customer has to wait in line, not including the actual checkout time? So now we're going to be looking at queue time with 10% fallout, 10% rejects. The coefficient of variability is still the same. So we've got 10% dropout rate from 30 customers per hour. And we have to figure out what's our time in queue time. And again, let's go, since we only got one resource here, I'm just going to use the simplified formula. I hope you don't mind, I'm going back and forth just to show you. And I'm going to use utilization prime here to show this, because we have a different utilization, because we have 90% of those customers coming in, and we have the same variability factor here. That hasn't changed because the variability of the inter-arrival times hasn't changed. So, but now we have a new utilization. That's what has been impacted here. U prime, it's going to be P over a new inter-arrival time, A prime, and essentially all we have to do here is divide it by 1 minus the dropout rate, and that brings us to 1.7 over 2 divided by 0.9. And U prime, the new utilization is only 76.5%. And we can plug that in. So now we have a TQ that works out to, I'm not going to write it all up, but that's going to be 11.39 minutes. Substantially different. So just by having 10%, 1 in 10 people not go through that checkout line, we cut the queue time not quite in half. If you remember, it was almost 20 minutes, 19.82 minutes. Interesting how big an impact that makes. So there's a question here. Can there be a scenario where utilization is 100%? The denominator turns to 0. How do we handle this scenario? That's a important point to make. Basically, this formula is telling you that when you have variability, if you're trying to get 100% utilization, things are going to blow up on you. And essentially, you are going to reach a point where your queue time eventually will become infinite, because you're going to continue to back up due to the variation in inter-arrival times and processing times. So very, very key takeaway here is that if you've got variability in your process, you cannot use 100% of the capability or capacity that you have. And that's a very key point. And in fact, if you look at the calculations you need to make for achieving a certain service level, I don't think we're going to do any problems dealing with it. Oh, maybe we have one of those tonight, but we'll see. There's a good section in the textbook about staffing to a certain service level. And it's very important, and it's very clear, and they've got a nice graph in the text that shows that in order to reach a reasonable level of service, in other words, for example, here we don't want people waiting 5 hours in the queue. We want to keep it down to a certain level. Um, it means that we really can't even get close to 100% utilization of our resource if we have variability here, and that's a key takeaway from this course actually. And so if there's a utilization that's near 100%, it says you're going to get people staying in line forever, or more likely you're going to get a lot of people dropping out because of that. And you're not going to be able to handle all the customers you have coming in. You're going to have to bite the bullet and hire more people. Good question, thank you. Next one, the store offers free popcorn and sodas for customers waiting in line. Well, maybe I'll wait 20 minutes if I get free popcorn. Every minute of waiting time costs the store 75 cents for these snacks. So what's the optimal number of employees at checkout? Their wage is $10 per hour. Now this one becomes a little bit more complex, a little bit more tougher to figure out. So we've got customers waiting in line, and we're giving them free snacks, but it costs us 75 cents a minute for those snacks. And the question is not what's it going to cost us? The question is how many employees should we have to minimize our overall costs? The more employees we add, the more we pay in wages, but the less we pay in food and drinks. So how do we do that? What do we do? How do we deal with that trade-off, right? So go back to economics. Essentially, we want to find out what's the partial derivative of the cost of waiting time with respect to the number of employees. That is this factor M. Don't panic yet. But we're going to look at the point where the marginal cost of the waiting, that is the amount of money we have to pay for the customers who are waiting, approaches but doesn't go below the marginal cost of the employees. And all of these are functions of the number of employees, right? I know you're cringing right now. Marginal cost for employees, going back to economics, it's $10 an hour. Wage rate, remember that? So we're not going to actually do any calculus here. We're not going to worry about it. But what we do want to figure out is what's the cost per waiting? What's the cost per employee? What's the cost per waiting for one employee, for two employees, three employees, and so on? And what's the cost if we have one employee, cost of wages for 1, 2, 3, etc. employees? So we'll do it kind of straightforward. But first thing we have to do is what is the waiting cost as a function of employees? So the cost of waiting, that is the cost of snacks, is 75 cents times the average inventory in the queue, right? That's going to equal 75 cents times the time in the queue times the arrival rate. And we can multiply all this out. Half of a customer per minute, that's the arrival, times the time in queue, minutes per customer. And I haven't put a number in there yet because that depends on M, the number of employees. Okay. So we'll just calculate this in terms of the queue time, and then we'll figure out what the queue time is depending upon the number of employees that we've got at the checkout. And this is per minute. Or, since we have wages in terms of hours, that's multiply that by 60, we get $22.50 times TQ per hour on average. This is the cost of supplying popcorn and drinks. And so what's the cost of waiting per hour? We're going to go ahead and take that 22.5 and multiply it by the queue time for different numbers of employees at the checkout counter. So we'll calculate queue time for one employee, and we already figured that out, 19.82. And we'll have to calculate the queue time for two employees, and that's going to be something, etc., up to as many as we need. Here's the formulas that that you need. Put it up here so it's don't make a mistake writing it. And I'm going to go ahead and calculate that cost of waiting for different numbers of employees. So what do we have here? Queue time. Well, let's go first. We have to calculate what the utilization is, and that's the second formula here. Utilization is processing time divided by inter-arrival time times the number of resources we have available. So I can go ahead and calculate that for each of these levels of staffing. You're going to have to trust me on my using the calculator here. You can go back later tonight and confirm that I did these right. And so it makes sense, right? The more employees you add, the lower the utilization. And notice, of course, that we start with one employee. We're only at 85% utilization, and we're still looking at 20-minute wait time. And 20 minutes times 75 cents, that's pretty costly wait time per customer. If we double the number of employees from 1 to 2, we'll cut that utilization in half, and so forth all the way down. I'm going to use those utilization numbers and now calculate the queue time for each of those cases. The original one with one employee, of course, was 19.8 minutes. Look what happens when we add a second employee, 0.88. These things have a big impact. Remember when we dropped out 10% of the customers, we cut that queue time almost in half just by cutting the customers by 10%. Clearly, this is not a linear function. Here, when we double the number of resources that we have, bringing the utilization way down in half, we cut the queue time by a factor of almost a 20, by 1/20th. Huge. And we go to 3, it works out to 1.162, and for 4 employees it's 0.0 039. Pretty big. Now we're going to calculate the cost of waiting per hour. That's multiplying by 22.5. That comes out to 445.95. Pretty expensive popcorn there. For 2 employees, it's 19.8. What was that? Next, might go away. For 3 employees, the waiting cost is $3.65, and for 4 employees, it's 88 cents per hour. And of course, the marginal cost for each employee is still $10 per hour. What's the marginal cost based on, as a function of number of employees, what's the marginal cost of the waiting? How do we do that? Remember way back when we looked at marginal costs in term 1? We can now look at when we change from 1 employee to 2 employees, what's the incremental change in cost for that, for 1 unit change in number of employees? Okay, so we'll take that 445.95 and subtract it from the 19.8. That's the marginal change in waiting cost per 1 employee at that level. So that becomes minus 426.15. Notice I put it between the two. It's the marginal change from 445 to 19.8. The next one, going from 19.8 to 3.65, is minus 16.15. If I did that calculation correctly. And then finally, going from 3 to 4 employees, the marginal cost, that is the change in cost, waiting time cost, for an additional employee, the waiting time cost goes down by $2.77. So now what's the optimal number? We want to make sure that the number of employees, the marginal cost of adding an employee doesn't exceed the marginal savings of that added employee. So we want to go as close to the marginal cost of $10 wage rate per hour per employee, but we don't want to go beyond that. We don't want to be spending more than we're saving. So we look at this table and see that the closest we can get to $10 without going below $10 is with 3 employees. So 3 employees is the optimal number. So by going from 2 checkout persons to 3, it costs us $10 more per hour, but we save $16.15 per hour when we do that, because we have less waiting, less popcorn, less soda. If we were to go to 4, it would increase our wage cost by $10 an hour, and we'd only save $2.77 an hour in popcorn cost. So we don't want to go to 4. 3 is the optimum. Okay, so I probably scared you by showing you the calculus, but don't worry about that. You're not going to have to deal with calculus in this class. But the idea, the concept is that but the cost of adding an employee should result in more than the cost for that additional employee in savings that you achieve because you added that employee. Easiest thing to do is build yourself a table, just do all the calculations. Obviously, not in an exam, you do it in Excel, but in an exam, you do it on paper. Everybody get this? I think this was a good question because it's kind of a key idea. I'm sure on the exam you're going to have something that deals with the amount of cost, or the cost that a change in process will result in. Any questions? No questions on that. Okay. Question. Could I explain how you got the 1615? Yes. Yes. So marginal reduction in cost of popcorn by adding one employee that is from 2 to 3 employees is going to be the cost of popcorn for 2 employees minus the cost of popcorn, actually the other way around. So the cost of popcorn for 3 employees minus the cost of popcorn for 2 employees. And that's going to be this number, 365 minus 19.80. So that's going to be, if I got room here, 365 minus 1980. So by adding that employee, I reduce my cost from 1980 to 365, and that works out to a reduction of $16.15. That's where that came from. Okay. This table should look exactly like something that you obviously remember from lecture in microeconomics, I think in the first week, looking at marginal cost. When we're doing it on this discrete basis. Okay, good. Okay, any other questions on this one? Fairly straightforward up to this last part. And then you have to do a little thinking there. Okay. Next one, question 8.6, Rent-A-Phone. Rent-A-Phone, new service company, provides European mobile phones to American visitors to Europe. They have 80 phones available at the Paris airport. On average, 25 customers per day wanting to rent the phones. They arrive uniformly throughout the 24 hours the store is open. Uniformly, what does that mean? This variation, but there's no seasonality to it. Remember, seasonality is a consistent change in the rate depending upon time, season, something like that. What this problem is telling us is that the average number of customers arriving around 9 a.m. is the same as, or roughly the same as the average number of customers arriving, say, at 5 p.m. So there's no variation based on time of day. It's all variation that's consistently varying through the day, through the time. Okay. And of course, 25 customers per day, 24 hours. That's a faster rate per hour than one customer per hour. Coefficient of variation is 1. Pretty much all of your problems are going to deal with a Poisson kind of arrival distribution, coefficient of variation of 1. Customers keep their phones on average 72 hours, and the standard deviation of this time is 100 hours. So all of these numbers kind of make sense, right? Given that Rent-A-Phone currently does not have a competitor in France, customers are willing to wait for the telephones. Yet during the waiting period, customers are provided a free calling card. Based on prior experience, they found that the customers incurred a cost of $1 per hour per waiting customer. Okay, very similar to what we had before. Now we're going to probably figure out, what's it worth to reduce the waiting time. So let's look at some of the key things here. I'm just going to summarize what we've got. We've got where am I? 8.6. I'm looking at the wrong problem. Okay. We have an inventory of 80 phones in stock and in the field. We have 25 customers per day, uniformly, 24 hours. We have coefficient of variability of the inter-arrival time of 1. Rentals last 72 hours on average. And they have a standard deviation of that time of 100 hours. And customer waiting costs us $1 per hour per customer. They're charging in American dollars, not euros. Interesting. Okay. So the way we're going to model this is we've got a queue. Customers sitting around the airport waiting to rent the phone if there's no phone immediately available. And then they're going to take it and they're going to use the phone. So this is 72 hours on average processing time. That's the model we're going to use here. And doing that, it's going to be very easy to get these numbers together. So we have 80 phones. That means we have 80 resources available for customers to be processing, using them. So now we have M equals 80, and you can see that this queue time is going to have a big factor of M in there. Our inter-arrival time, we're going to just do some conversions here. It's 1/25 days per customer. That is 25 customers in a day. So the inter-arrival time in hours is going to be multiply that times 24 hours per day. And in terms of hours, it's going to be 0.96 hours in between customers, inter-arrival time. We know the coefficient of variability of that is 1. We know our processing time is 72 hours. Coefficient of variability for the processing time is going to be the standard deviation of that processing time divided by the time. So it's 100 divided by 72. And using the calculator, that works out to 1.389. And then finally, I know I'm going to need utilization in order to calculate what my queue time is. So that's going to be processing time divided by inter-arrival time times the number of resources we have available. That's 80. And that works out to be 0.9375. So we've got 72 divided by 0.96 times 80. That gives us a 0.9375 utilization. Close to 94% utilization. Just intuitively, you should think now, based on that earlier question about 100% utilization, at 94% utilization, we're going to have a lot of people waiting for a phone. Even though we've got 80 phones and only 25 customers a day, they're going to be using most of the phones, and so customers are going to be waiting a lot due to the variation in times. So what's the average number of telephones the company has in its store? Well, now this is interesting. Average number of telephones. So we're going to be talking about an inventory here. The way I'm going to approach this is I'm going to figure out how many phones on rental. And then I'm going to figure out how many are left behind. So the inventory of phones on rental out in the field in the processing stage is the time times the rate. And why am I doing this? Because I know what these numbers are. And that's going to be P, processing time, times the rate, 1 over A. And that works out to 72 times 1 over 0.96. And that's 75 phones rented on average. Okay. Why didn't I directly calculate the number of telephones the company has in the store? Because I don't know the times there. So the in-store inventory is what's left. And so we've got total of 80 resources available minus the 75 that are in use. That equals a total of 5 phones in store on average. Okay, so on average, we've got 5 phones in the store sitting around waiting for a customer to come by, on average. How long does a customer on average have to wait to get a phone? So this is a little counterintuitive, right? You've got, on average, you've got 5 phones sitting there waiting to be rented, but you've got customers waiting for phones to be available to rent. This is all due to the fact that you've got variability in the time between customers and the time in processing. That is, how long does a customer keep the phone out on rental? So the wait time, again, we've got the this nice little queue time calculation based on multiple resources, and I'm going to go ahead and plug the numbers in there. We have 72 hours of processing time. We have 80 resources available. Our utilization is pretty high, 0.9375. almost 94%, and we're going to raise that to the power of 2 times 80 plus 1, that's 162, square root of that, minus 1, that fancy formula, and then 1 minus the utilization, 0.9375. That's our utilization factor, and then we'll look at the variability factor. 1 squared plus 1.389 squared over 2. So that's the coefficient of variation for the inter-arrival time, which is 1, Poisson distribution, exponential rate, Poisson arrival. Coefficient of variability of the processing time is 1.389. We calculated that earlier based on the standard deviation on the time that customers use the phones. Average those two numbers, plug it in, and we have a queue time on average of 9.89 hours. Incredible. We're sitting around in the airport for almost 10 hours waiting to rent a phone. Ouch. And yet, on average, we've got 5 phones sitting there waiting to be rented. You can see that because of the variability, sometimes a customer will come in, there'll be a phone available, they'll be able to walk out right away. Sometimes, and in the worst case, customers walk in, and a lot of customers will walk in, and there'll be no phones for a long time. On average, there's no phone sitting there for 10 hours. No phone there for 10 hours. How does this company stay in business? I don't know. Okay, and of course, notice that it cost us something to have the customers waiting. What are the total monthly expenses for telephone cards? So we're going to give a card to the customer while they're waiting. I don't know how they're going to use this, but it'll be $1 per hour per customer that it costs us. We've got 9.89 hours of waiting times 25 customers per day times 30 days times $1 per hour per customer. That equals, plug that into the calculator, $7,420.65 expense for keeping the customers happy with free phone calls. 94% utilization, huge, heavy cost when we have to pay to keep those customers happy. Okay, assume they could buy additional phones at $1,000 each. Is it worth it to buy one additional phone? So again, similar to the previous problem, what's our marginal value to that? What's our marginal improvement in cost for customers waiting? What's this going to hinge on? We haven't changed variability. All we've changed is the number of resources we have available. So now M is 81. So we can go ahead and figure out what the costs are going to be. And fortunately, we don't have to look at adding 1 phone, 2 phones, 3 phones, another 100 phones. We only have to answer this for 1 additional phone. So the new utilization will be 72 processing time divided by M times the inter-arrival time. And that's going to work out to be 0.926. So we've only dropped utilization by almost, roughly 1%, adding 1. But now what's the queue time? And it's going to be 72 divided by 81 instead of 80. Now the utilization factor is going to be a little bit different. And now the exponent will be a square root of 164 minus 1, and the bottom will be 1 minus 0.926. So that's going to change things a little bit. The coefficient of variability term is not going to be impacted. That'll be the same. Plug that in, and we have 7.10 hours. We went from 9, almost 10 hours down to 7. So we're more than 2 hours less waiting. And the cost now is 7.1 hours times 25 customers times 30 days times $1. That's going to be $5,324. So basically, $1,000 phone saves $2,097. So from $7,420, we reduced that down to $5,324. That's a savings of $2,097. So yes, buy at least one new phone. And you can see the tremendous cost of a high utilization of around 94% for these resources. And clearly you can kind of extrapolate this even further, and intuitively you can see that you should probably buy a bunch of phones and have far more phones available than you would typically have rented out in order to minimize the waiting time, minimize the out of stock time, and the cost that an out of stock situation gives you. Okay, we've got one more part to this question. How would the waiting time change if the company decides to limit all rentals to exactly 72 hours? No variability at all. Assume that if such a restriction is imposed, the number of customers requesting a phone would be reduced to 20 per day. So we're changing two things. We're changing the number of customers coming in, that is the arrival rate, and we're changing the variability of the processing time, the rental time, down to 0. So now processing time is still 72, but the standard deviation is 0. And now we have 20 customers per day. What's the time in the queue? Coefficient of variability for the processing is again 0, right? P is 72. Coefficient of variation for the processing time is 0. A, the inter-arrival time, is now 24 in 20. 1.2 hours, so it's 20 per day. That's 20 per day coming in. 1 over 20 times 24 hours is the arrival time in hours. The coefficient of variability for the arrival time is unchanged at 1. Our new utilization here is P divided by M times A. That's 72. We're still working with 80 phones. Inter-arrival time of 1.2 hours. Utilization is now 75%. haven't made a major change in the number of customers, but we've made a big change in the variability of the number of hours they rent things for. Queue time, 72/80. That's not changed. Utilization has changed. Here's the big change. That big factor now is 1/2. So we got 0.9 times 0.137 times 1/2. The queue time is now 0.06166 hours. Much, much less than the 10 hours we started with. And this is mainly due to reducing the variability in the processing time. So you can see how huge an impact variation has. Now, if you could only limit customers exactly to exactly 72-hour rentals, it's kind of like the Blockbuster deal. If you go 1 minute over 72 hours, you have to pay 10 times the amount for the rental. Anyway, any questions on that one? As you can see, as we go through these, we're adding a little bit of a wrinkle each time. And the questions, each of them are a little bit different. They're asking for maybe wait time versus the total time, subtleties like that that you have to be very careful about when you are working through an exam. Okay, let's move on to a new kind of problem, and this is from chapter 9, where we talk of the impact of variability on systems where we don't have customers willing to wait. In other words, we don't have a queue. If a demand comes in to our process and the process is not available, that demand is lost. So this is the other end of the spectrum, where we have no waiting time, no queue, and we have losses based on the variability of incoming rate and processing time. So 9.1 is a pretty simple problem, but it kind of illustrates the issues here. Flow units arrive at a demand rate of 55 units per hour. We don't know what they are. It doesn't matter. That this is a general process. It takes on average 6 minutes to serve a flow unit. So the demand rate is 1 over A, right? Inter-arrival time is 1 over the flow rate. 6 minutes to serve, that's P. Service is provided by 7 servers, so M equals 7. We've got some questions. What's the probability that all 7 servers are utilized? How many units are served every hour? How many units are lost every hour? Okay, now we have some different things we're being asked. We don't ask about queue time because we have no queue. But now we're asking, what's the probability that we have a request coming in, demand coming in, but no server available to handle that demand? That's the case where that demand is lost, it goes away. So we have flow rate 55 per hour, processing time 6 minutes on average, 7 servers. Let's go ahead and calculate our utilization. And we've got a demand rate of 55 units per hour. And what's the capacity? We've got 7 servers. times 10 units per hour. That's 1/6 minutes, right? So our processing time is 6 minutes. That's 0.1 hours. The capacity is 1/p, and that's 10 per hour. And that implied utilization comes out to be 78.6%. Not too bad, but you can see with variation, we're going to lose a lot. Okay. Here's the deal. Now we can go with this information, we can figure out what our loss probability is going to be. And how does this work? Well, fortunately, we've got this guy, Danish guy, who figured this all out based on a Poisson arrival distribution. So we've been using that all along here, and essentially a normal processing distribution, although that's less important than the arrival time. But he figured this out, Erlang, and he came up with this fantastic formula to figure out what the probability of loss is based on not having a resource ready when the demand comes in. This fancy thing with lots of factorial numbers and things like that. Don't ever try to calculate it. There's a table. You'll have that table provided. So you go into the Erlang loss table. So if all 7 servers are busy, we will lose our customers. And so what we want to do to answer this question is find the probability with M resources and the R variable, which we'll get to in a moment, using the Erlang loss function. R is basically the ratio between the processing time and the inter-arrival time. It's just a parameter, the ratio of those, that's used in this loss function. M is 7. We know we have 7 servers. And the processing time is 0.1 hours. A is 1/55, or 0.018182. Why did I do that? So many decimals. I don't know. So P over A is this R parameter, and that works out to be 5.5. And I'll note this is the same as utilization times M. The same 3 numbers are used all over the place. So now let's go to the table. And we'll go in row and column, finding the probability, capital P, based on 7 resources of an R value, or a ratio of processing time to arrival time, of 5.5. And that loss probability is 0.1525. Okay. Notice what didn't show up here. First thing, the coefficient of variability for the inter-arrival time is assumed to be 1. So that's given in the formula. The other thing that we didn't have to supply here is the standard deviation of the processing time. That doesn't seem to have any impact on this loss. So that's an interesting thing to remember, and we'll see what the impact of that is in a little bit. So anyway, that's the probability that all 7 servers are utilized at any point in time. Next, how many units are served per hour? And that's, in other words, that's basically what's the flow rate. And in order to calculate that, basically, what's the arrival rate? What's the demand rate? And then we have to reduce that by the fraction that are lost. So we can calculate that as the arrival rate, that is the demand rate, times the fraction of demand not lost. And so that's going to be the arrival rate is 1 over the inter-arrival time. And it's going to be what fraction are not lost, the probability of loss. That's going to be 55 times 1 minus 0.1525, sorry. And that works out to 46.613 units served per hour. So notice we have 55 coming in, but we're only able to handle 46, almost 47 of them in each hour. So we're going to lose a whole bunch. How many units are lost every hour? Well, the number of units lost is going to be 1 over A, that is what's the flow rate coming in, times the probability of loss. That's going to be 55 times not 1 minus 0.15, but 0.15, probability of losing. And so that means that 8.388 units lost per hour. Pretty straightforward application of the Erlang loss function to a variable system, variable processing, and no input queue, which means that any demand that's not able to be satisfied will be lost and will be diverted, or customers will go elsewhere, something like that. Okay, very simple application of this other extreme, variability causing a loss of demand. Any questions on that one? What's the next one? 9.4. Oh, this is a fun one. Okay, if we got no questions on that, let's go to the next one. And this one's interesting. I like this one. We have Mr. R.B. Cheney, who owns a large gas station on a highway in Vermont. In the afternoon hours, there are on average 1,000 cars per hour passing by. 1,000 cars per hour. 2% willing to stop for gas. However, there are several other gas stations with similar prices on the highway. Potential customers are not willing to wait, and they'll bypass his gas station if the gas station is full. They have 6 spots, 6 pumps that can be used for filling, and it takes a car on average 5 minutes to fill up his car and do whatever else he has to do. What's the probability that all 6 spots are taken? In other words, if all 6 spots are taken, then the customer will bypass the station and go somewhere else. That's a loss, demand lost. And what's the probability that all 6 spots are taken given these parameters? And then how many customers are served per hour? Same idea here. Of the customers that are coming in, some are lost, some are not lost. How many are left that aren't lost? The wrinkle here is we don't actually know, we're not given directly the number of customers arriving. we've got to figure that out. So we have a situation here. We got a highway, and we've got 6 gas pumps, and the time taken at each one is on average 5 minutes. Customers come in, they drive in, and they're coming at a rate of 1,000 cars per hour, 2% of which will pull in for gas. They will come in and they'll pull up to an open pump, an available pump, and then head back out to the highway after 5 minutes. However, if they go by all 6 pumps and they find that none is empty, they'll bypass them all, and these are lost customers. So that's the scene. That's what's going on here. So basically 1,000 cars per hour, that's not the rate that we have coming into the gas station. We only have 2% of those. And then we've got 6 pumps. Takes 5 minutes to process at each pump. We're going to have some losses when all the pumps are full, and we're going to have to figure out all those numbers. So what's the probability that all 6 spots are taken? Well, the first thing we have to do, of course, is find the demand. And that's going to be based on that 2%. So it's 2% times the 1,000 cars per hour that are coming by. So this 2% of those would like gas. They're not driving Teslas. And that works out to 20 cars per hour would like gas. And that is the flow rate for demand, or 1 over the inter-arrival time. So our A is 0.05 hours per car, or if we convert the units, 0.05 times 60, or 3 minutes per car inter-arrival time on average. Now we have to find the probability based on that. So let's find the probability of all 6 being occupied. That's this Erlang loss function. We've got m equals 6, r equals p over a, and that's the same as the utilization times the number of resources available. We know that the processing time is 5 minutes per car, and we just calculated what the inter-arrival time is 3, and that's minutes per minute. So R is 1 2/3. We go and from the table, we use R and M. So the probability of with 6 resources of an R ratio of 1.667. That becomes, if we look it up, is 0.0056, or a 0.56 percent probability of loss. Make sense? Now, it's a little bit more reasonable loss than we had in the previous problem. Next question, how many customers are served per hour? This is also known as the flow rate, with losses accounted for. So we have to reduce the demand rate by the losses to get the flow rate through the system. So the flow rate equals the demand rate times the probability of a pump being available, a free pump. Okay, which is 1 minus the probability of all them being full. Demand rate is 1 over the inter-arrival time, and the probability of free pump is 1 minus the probability of loss. That is the probability that all 6 pumps are taken. So 1/3 times 1 minus 0.0056, that calculates out to 0.3315 cars per minute. Multiply that by 60 minutes per hour, you get 19.89 cars per hour served. Don't forget your units. Don't go providing it cars per minute if they're asking for cars per hour. Pretty straightforward. Again, the only real challenge here, once you know how to use the Erlang table and figure out what the loss is and what the parameters are, is the challenge for this one is making sure you got the right numbers for each of the parameters. So the arrival rate, or the demand rate, is only 2% of the 1,000 cars driving by. So you've got to multiply 1,000 by 0.02. 1 over that gives you A, the inter-arrival time. Any questions? Moving right along here. Go to something a little bit more complex, not too much. Again, Chapter 8, we had variability that caused waiting, people to wait, and people were willing to wait forever. And we saw how higher utilization numbers caused a lot of waiting time. Here we're at the other extreme in Chapter 9. Problems here, we're dealing with situations where we can't wait for some reason. There is no input queue, there's no waiting. And the consequence of that, of course, is you lose some of that demand. And of course, variability is the problem here, the devil. And so basically all of these kinds of problems are going to be similar. You're going to have to figure out what the loss factor is. What's the probability of loss? And then apply that to solving the question that you want to find out. So here we have Extremely Fast Service Incorporated. Extremely Fast Service is a call center with several business units. One of its business units, Fabulous 4, staffs 4 operators. They work 8 hours a day, Monday through Friday. Customer support for a mail order catalog company. Customers call during business hours, and on average, a call arrives every 3 minutes, with a standard deviation of 3. So again, CV of 1, you do not have to consider any seasonality in this call arrival pattern. In other words, it's kind of variable but uniformly distributed. The average and